All right, I've got about 30 minutes. I'm going to see how much I can do in terms of the rest of 8.5 or 8.5, which was our power series homework. And I believe I stopped on 11. So I'm going to start number 12. And see what happens. All right, so number 12. Of course, all these markers are junk. I don't know why they keep putting these back into the faculty lounge area if they don't work. All right. Oh, where's my mark? Don't go past that. Don't go past that. Okay. This one also doesn't work. Unbelievable. And that one doesn't work. Okay. Sum n equals 1 to infinity of x to the n over 5 to the n times n to the 5. It's getting very frustrating with these markers. All right, so ratio test. So I'm going to do my ratio test here. Take my limit as n goes to infinity. This marker doesn't work either. Of, let's see, plug n plus 1 in here. X to the n times x. You've got to be kidding me. Over 5 to the n times 5. Times n plus 1 to the 5th power. That's just replacing all of the n's with n plus 1s. We've done this so many times now. And then I do that flipped over. So 5 to the n, n to the 5th, it's multiplication, and then x to the n down here. And I get some cancellation here, 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 here. And then I'll start to group together all my n stuff and then all my x stuff. Separate those. So, oh, and I want this to be less than 1. So I have the limit as n goes to infinity of, let's see, I have n to the 5th here. On the bottom, I have a 5 and I have n plus 1 to the 5th times, and then I have just an x. I need that to be less than 1. So you can see that when I take this limit right here, I get infinity over infinity. One thing I can do, since these are both to the 5th power, I could rewrite this as, this is 5 on the bottom, so how about 1/5 times, and then since these are both to the 5th, n over n plus 1, both of those to the 5th, times x, absolute value, need that less than 1. And then now if n goes to infinity, and here you have infinity over infinity, you can do L'Hopital on just the inside. You get 1 over 1, that's 1, and 1 to the 5th power is still 1. So all of that's going to turn into a 1. And so I have 1/5 times x. I need the absolute value of that to be less than 1. And so now what I can do is rewrite this as 1/5 absolute value times absolute value of x. I need that less than 1. But the absolute value of 1/5 is just 1/5. And now I multiply both sides by 5. Absolute value of x needs to be less than 5. And so my radius of convergence is this number right here. And my interval is going to be, at least right now, my interval is going to be x must be less than 5, greater than -5. And then what I need to do is check the endpoints. So let's check those. Let's check. I'll do -5 first. So I rewrite my sum. N equals 1 to infinity. It was x to the n, so that's -5 to the n. And then it was over 5 to the n times n to the 5th And if I rewrite this, sum n equals 1 to infinity, and I take that and I split this up to be negative 1 to the n times 5 to the n, then I'll get negative 1 to the n. This 5 to the n that I get from that will cancel with this one, so it's over n to the 5th. And this one is an alternating series. I can do the alternating series test. I'll do the second thing first. Right here, that's my b sub n. So the limit as n goes to infinity of that piece, 1 over n to the 5th, does equal 0, that's good. And then the first thing I'm supposed to show, or the other thing, is that it's decreasing. And that's obvious because if I take 1 over n to the 5th, that is bigger than 1 over n plus 1 to the 5th. You can do the work if you want with that, but it's obvious that this denominator is bigger than this one. So this fraction is smaller than that one, so that checks. So it's going to converge by the alternating series test, which means I do want to include negative 5. So I'm going to put this right here. And now I'm going to check 5. So when I check 5, that changes. This is now a positive 5 right there. I no longer have to split off that negative 1. These just cancel. And we get sum n equals 1 to infinity, 1 over n to the 5, or 5th power. This is a p series. P is 5, which is greater than 1, therefore it converges. And that means I do want to include that endpoint also. So my interval of convergence is the closed interval negative 5 to 5. All right. I'm going to go try and get another marker.
Yeah, like
Seven markers that I took out of the faculty room. Let's see if any of these work. I doubt it. I'm gonna have to talk to someone about this. All right, what do you think? Think this is gonna work? I doubt it. 13. Oh my goodness. This is almost laughable now. 13. I'm starting to get really upset. Sum n equals 1 to infinity of negative 3 to the n over n root n x to the n. So that x to the n is really on the top. I'm going to do my ratio test here. So limit n goes to infinity. All right, n plus 1s, remember this is really up top. So that's negative 3 to the n times negative 3 to the first power, and then x to the n times x over the denominator with n plus 1 plugged in. Feels like I did this problem already, but. And then flip it, flip that up there, get up, get that. And then negative 3 to the n, x to the n. I need that to be less than 1. So here, 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 here. And so what I'm left with is the limit as n goes to infinity of, okay, my n stuff here, n root n over n plus 1 times root n plus 1. Now I also had a negative 3 up there. I'm going to just put that negative 3 right here, and then I'm going to put my x right there, and then less than 1. So I've got to figure out what's happening with all those n's first. And yeah, I have done something similar to this. So n goes to infinity, n over n plus 1. I'm going to split that from these two roots. I'm going to put both those into one root like that. Then negative 3x less than 1. And then limit n goes to infinity, you get infinity over infinity. L'Hopital once here, you get 1. Inside here, same thing. L'Hopital once, you get 1. Square root of 1 is 1. So all of this here is going to 1. So all I'm left with is negative 3x, absolute value less than 1. Then I pull the negative 3 away from the x using properties of absolute values. The absolute value of 3 is actually, the absolute value of negative 3 is just 3. So this is really 3. Absolute value of x is less than 1, which means that the absolute value of x is less than 1/3. So my radius of convergence is 1/3. And now I need to check my interval. So far my interval is x must be less than 1/3 and greater than negative 1/3. But make sure it's coming out on the camera. Yeah, it's coming out. All right. So I need to check my two endpoints now. And I'll do that into the original series. So first, I'll do negative 1/3. Let x be negative 1/3. Sum n equals 1 to infinity. So this is a different brand marker. And they do well, but they don't last very long. Let's see, so I've got negative 3 to the n over n root n. And then over here, x to the n. But I said that was on top, so I'm just going to put it on top. But x is negative 1/3 to the n. And if I do those two together, I get sum, I'm an n 1 to infinity, I'm not going to write that anymore. Put these two together, negative 3 times negative 1/3 is positive 1. Both of them to the n, so 1 to the n is just 1 over n times root n is n to the 1/2. And this is really just sum 1 over n to the 3/2. That's a p series. P 3/2 greater than 1 converges. So I know if x is negative 1/3, it converges, so I want to include that. And now I change it to positive 1/3. If I change that to positive 1/3, this becomes this. And now I have a problem because when I put those two together, I don't get 1, I get negative 1. So this is actually going to be negative 1 to the n. And this is an alternating series. And I'll actually change this down here to n to the 3/2. So this is an alternating series. So alternating series test. Here's my b sub n. Okay, and you can check that the limit as n goes to infinity, 1 over n to the 3/2 does go to 0. And then the decreasing thing, I need 1 over n to the 3/2 to be greater than 1 over n plus 1 to the 3/2. And again, checking that this is bigger than this, so this checks. So it'll converge. So I have to include both endpoints. So the interval of convergence is the closed interval negative 1/3, 1/3. All right, that was number 13. Okay, now number 14. Oh, here we go. Sum n equals 0 to infinity. Negative 1 to the n. X to the 2n plus 1. Haven't seen that yet. Over 2n plus 1 factorial. All right, let me do a ratio test here. Limit n goes to infinity. Carefully plugging in n plus 1. So remember, this is really like one big fraction like that. So I have negative 1 to the n plus 1. I don't split that up because I know it's going to go away with the absolute value. Here, be real careful. You're plugging in n plus 1 right there. So that 2 is going to distribute to both. So you actually get x to the 2n plus 3 when you plug n plus 1 in there. So you get x to the 2n times x cubed, like that, over, so that's taking that and splitting it up. Then, on the bottom, you have to plug n plus 1 in right there. So you're doing 2n plus 1, all of that factorial. Again, you're going to get 2n plus 3. Factorial. And then you're going to multiply by that thing reciprocated. So 2n plus 1 factorial up here. On the bottom, negative 1 to the n. And then over here, x to the 2n plus 1. Which I'm actually going to change because I want this to cancel. I'm going to change that to x to the 2n times x. Need that to be less than 1. All right, these don't matter. This is canceling. These don't cancel, all right? So what I need to do is I need to rewrite that 2n plus 3 factorial. I'm going to start peeling off. 2n plus 3, 2n plus 2. I'm going to get it down to this. 2n plus 1, and then the rest of the way is the factorial. So when you do that, you can see that, don't worry about that anymore, this and this cancel, so what you're left with is this right here. So now my new limit looks like this. I have limit, n goes to infinity of all my n's first. Well, I just have a 1 on top. And then the other things with n right here. 2n plus 3 times 2n plus 2. And then as far as x's, I have x cubed and x. And when I put those together, I get x squared. I need this to be less than 1. Now, if I let n go to infinity, I do not get infinity over infinity. I actually get 1 over infinity, and this goes to 0. And since that goes to 0 times x squared, if I want that to be less than 1, that's always going to happen. No matter what x is, if this thing gets arbitrarily small, no matter what x is, I square it, multiply it times something very small, that's going to eventually be less than 1 for large enough n. So that means that this is going to converge always. So what does that mean? Well, that means that our radius of convergence is infinity, and it means that our interval of convergence is every real number x. So everything on the real number line. I like it when that happens because you don't have to test endpoints. Okay, 15. Sum n equals 0 to infinity, x minus 2 to the n, have not seen that before, and then over n squared plus 1. So this is a power series, and remember when we said we had x minus a to the n, we'd say it was a power series about a. So this is a power series about 2, and let's go ahead and set up our ratio test for this. Limit, n goes to infinity. Let's see, plug n plus 1 in right there. You get x minus 2 to the n times x minus 2 to the first power, which I'm not going to write, over n plus 1 squared plus 1 times that flipped n squared plus 1 over x minus 2 to the n. I need that to be less than 1. So this cancels with this, and that's all the canceling I can do at this point. So I'm just going to rewrite this, limit, n goes to infinity. All right, all my n's. So n squared plus 1 here on top, And then on this one, I'm going to actually FOIL that out. We did this in class. And then add 1 to it. So I get n squared plus 2n plus 2 times, and then in terms of x, all I'm left with is that factor. And make sure you put it in parentheses because it's being multiplied. I need that to be less than 1. And on this, infinity over infinity, if you do L'Hopital on that twice, I believe, you're going to get 1. So since that goes to 1, then this limit is equal to absolute value, is going to give us, this left side is going to give us the absolute value of x minus 2 must be less than 1. And that is what we're trying to get. Remember, to find the radius of convergence, you have to have it look like this. And that's what we have. So my radius of convergence right now for this problem is 1, this. But to get the interval, I need to turn this into inequalities. So this minus 1, but then greater than negative 1. And then I'll add 2 to everything. When I add 2 here, I get 1. When I add 2 here, I get x. When I add 2 here, I get 3. So that's my interval of convergence so far. Now what I need to do is test the endpoints. So let me test 1 first. If x is 1, let's see what this series turns into. If x is 1, I plug 1 in here, I get negative 1 to the n over n squared plus 1. And for this, I think I'm going to stop doing all the work for this. This is an alternating series test problem, and it's pretty easy to show the two conditions. So this will converge. All right, that means I do want to include negative 1. What did I do? X was negative. No, x was 1. Sorry, I was looking at this. X was 1. So I do want to include that. Now let's let x be 3. If x is 3, then that changes things. If x is 3, this is 3 minus 2 is 1, so now no more alternating series. And for this one, you could probably do a comparison. I did something like this in class. Compare it to like 1 over n squared. And maybe the limit comparison. So call this a sub n, call this b sub n. Use the limit comparison. That means you set up the limit, n goes to infinity of a sub n over b sub n, and then show that this is going to be some constant, some positive constant. And it'll turn out to be 1. So that means whatever this one does, that one does. And this one is a p series, p is 2, it converges. So we should include both endpoints. So our interval of convergence is the closed interval 1, 3. All right. Let me do at least through 16. Sum n equals 0 to infinity, negative 1 to the n, x minus 3 to the n over 2n plus 1. All right, let's do our ratio test. For the ratio, limit n goes to infinity. All right, n plus 1 in there, so negative 1 to the n plus 1 times x minus 3 to the n plus 1 is x minus 3 to the n times x minus 3. On the bottom, I have 2 times n plus 1, which is really what? 2n plus 3, right? 2n plus 3. And then times that thing flipped, so 2n plus 1 up here. Over here I've got negative 1 to the n, which won't matter. X minus 3 to the n, I need that less than 1. So start canceling stuff out. These don't matter. And so where we are is limit, I keep writing equals. Limit n goes to infinity. Absolute value. Okay, let's get all our n stuff together. Got 2n plus 1 here, 2n plus 3 here, times, in terms of x's, I just have x minus 3. I need that to be less than 1. That the factor over there with n's in it is an infinity over infinity, L'Hopital. You get 1. So you get absolute value of x minus 3 is less than 1. So I've got my radius of convergence right now. It's 1. And then when I do the inequality, x minus 3 is less than 1, greater than negative 1. I add 3 to everything, so I get 2 less than x less than adding 3, so 4. So I've got to check those endpoints. So let's let x be 2. Sum n equals 0 to infinity. Okay, negative 1 to the n times x minus 3 to the n over 2n plus 1. So if I let x be 2, this sum becomes negative 1 to the n times 2 here. I get another negative 1 to the n. Then I'll just do the whole thing over 2n plus 1. And then I can put those two together. That's just a 1. And that's a harmonic series. And that diverges. That means I do not want to include 2. Okay? Divergent harmonic series. But if I make this a 4, then when I do this, this is not negative 1 anymore. It's positive 1. And when I put those two together, I do get a negative 1 to the n. And this is an alternating series. And you could show the two conditions. And when you call this b sub n. So 1 over this part. Obviously, it goes to 0 when you let n go to infinity, and then it's also decreasing. So when you check those, it'll converge. That means you do want the 4. So our interval of convergence is the half open or half closed interval, 2 to 4, but include 4. All right. Let's see. Just maybe one more. I'm going to do 19. I'm skipping 17, 18. Let me do 19 and see what happens. It just looks interesting. I'll put a mark here that maybe I'll come back and do 17, 18. Sum n equals 1 to infinity, n factorial, 2x minus 1 to the n. So if I try a ratio test on this, limit n goes to infinity, I get, since there's not a fraction, I'm just going to write n plus 1 factorial, 2x minus 1 to the n times 2x minus 1 over this, n factorial 2x minus 1 to the n. I need that to be less than 1. Also, we're going to notice that n plus 1 factorial is n plus 1 times n factorial. These n factorials cancel, these cancel, and so you're left with limit n goes to infinity of, let's see, I have an n plus 1, and then over here I have a 2x minus 1. I need that to be less than 1, but the problem is that as n goes to infinity, this gets infinitely large, and I can't control it, so this is going to blow up. The only way I'm ever going to have any control of that is if this is 0. So if I let 2x minus 1 be 0, that means x is a half, then this doesn't matter anymore because that is 0. No matter how big that starts to get, times the number 0 should be less than 1. So if I let x be a half, that's the only time it's going to converge. So in this problem, whenever we have a single point, it's being the only place we converge, we say the radius of convergence is 0. And we say the interval is actually the single point 1/2. We call this a singleton. Singleton. Just a single number. I want to keep going. I still have some time. Let's try 21, because that one looks interesting. We haven't done one of these in class. I did do something like this before on one of the previous sections, homeworks. It's because the formula is kind of weird, all right? They give you sum, n equals 1 to infinity, and we've got x to the n. Let me mark what I skipped here. I did 19, I skipped 20. Okay, and then on the bottom, they have this thing, remember this from the homework, a pattern? 1 times 3 times 5 times all the way till you get out to 2n minus 1. So like, just for example, what this would look like, if I let n be 1, I'd have x to the first power over, and then I'm going to go 1 times 3 times 5. I'm going to multiply odd numbers together until I get to, let's see, 2 times 1 is 2 minus 1. That's 1. So I'm only going to have the first odd number. And then plus, now I do, n is 2, so x squared over. Now I'm going to do 2 in here. 2 times 2 is 4, minus 1 is 3, so I'm going to go 1 times 3. The next one will be x cubed. This time, 2 times 3 is 6, minus 1 is 5, so I'm going to go 1 times 3 times 5. Next one, x to the 4th over 1 times 3 times 5 times 7, and so on and so forth. We want to know if, for what values of x will this converge. That's just to give you an idea of what it looks like. So now, I'm going to do a ratio test, but I have to be kind of careful with it. Limit, n goes to infinity. All right, the top's pretty clear. X to the n times x. That's what happens when I plug in n plus 1. But down here, 1 times 3 times 5 times dot dot, I have to plug n plus 1 in there. And so I get 2n plus 2 minus 1, which is 2n plus 1. And if you remember from the homework we did before, I put that here, and then in front of it, I put the one that would be right in front. And because each of these, you know, to go backwards, you just subtract 2, subtract 2. I'd subtract 2 from this, and I'd be back at 2n minus 1. Now, I did that in the previous homework because it helps me with cancellation. So over here, I need this less than 1. It's just that flipped over, 1 times 3 times 5 times dot 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 2n minus 1, and then on the bottom, x to the n. And so you can see that all of these, you know, 1, 1, 3, 3, does this look familiar? 5, 5. All these cancel until I get that, and the only thing left is this one. Then the x to the n's cancel. So this gives me limit, n goes to infinity of, let's see, what's my n stuff? The only thing left with n is this one on the bottom. And then the x, the only thing left is this. Oh, awesome. Is that n goes to infinity, this goes to 0. And so no matter what I pick for x, that's going to be less than 1. So this is one of those problems where your radius of convergence is everything, because it doesn't matter what x is, and your interval of convergence is the entire number line. Okay, that was number 21. So I'll offer you a bonus problem. Okay, and I guess the only way you'll know is if you do this video. And here's what I'm going to offer. Today is, let's see, I just lectured on power series yesterday. So for bonus, do number 22, which is the sum n equals 1 to infinity of n squared x to the n over 2 times 4 times 6 times dot 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 to 2n. That's very similar to the previous problem. This will be due the next time we meet, which would be, well, I want to make this video kind of vague for future semesters, but let's just say I just lectured on power series. So the next class meeting, if you turn this in at the beginning of class, I'll give you a nice little bonus on one of your exams. All right? A nice little bonus is relative. It might be nice to you. To me, it may not be nice to you. It depends how you look at it. So there are a few other problems in this section that I haven't done, that I skipped, that I may come back and do. I think you have enough from what you've seen to do those problems, but this should be enough to get you through all the homework I assigned, all right? Okay, guess that's it. I'll post this right now.